Okay, so good evening everyone. Uh, Let us begin. Is there anyone who is joining for the first time?
Yes, sir.
Okay, Srujana. Okay, so Srujana, could you go through the previous session recordings?
Yes, sir. I listen.
Okay, okay, fine. So let us see, like, if you have any queries, please feel free to interrupt and ask. So we are in the fourth week of this course, and let us begin. Where we left last time, it was, I think, around the distributions, right? Probability distributions.
Ah, yes, sir. Yes, sir.
Yes. So we'll just continue from there. We'll do a brief recap of what we discussed last time, and then we'll go on to discussing probability distributions and different types of distributions. And I think we touched upon binomial distribution last time, so we'll discuss other distributions as well and solve some problems in Google Colab. Okay. Meanwhile, let me just join from my iPad so that I can share my screen as well. Any queries? Meanwhile, any queries from the previous class? You may ask it, like, even if it is basic query, please feel free to ask. Okay. Uh, Sorry for that. Like, I'm trying to join from my iPad. Please wait for a minute. Okay, great. Are you able to see my screen? iPad screen?
Yes, sir.
Okay, great. Fine. So, in the last class, we touched upon the topic of distribution. First of all, we discussed what random variable is. So, can someone explain what random variable is?
The outcome of the random experiment is known as a random variable,
Not
sir.
really, not really. So a random variable is basically, it acts like a function. So variable is a misnomer for that. So any random process, for example, any experiment or random process like tossing a coin, it generates certain outcomes. But these outcomes may not be numerical in nature. For example, tossing two coins. So tossing two coins, the sample space is HH, HT, TH and TT. So here the outcomes of this random process or experiment are heads, tails. These are not numerical in nature. So what random variable does is, it depends on the definition of the random variable, how you define that. It takes these inputs and map that to some numerical value. Okay, for example, let's say a random variable x is number of tails. So for HH, okay, sorry. So what all values can x take? X take. It can be 0, 1 or 2. So what is the probability? Okay, forget about the probability first. In how many cases x is 2? X is number of, I am defining the random variable x as number of tails. So how many instances are there where x is 0? That is, the number of tails is 0. Anyone?
Only one?
Yes, and that is this HH case. And then x equal to 1. X equal to 1 means there is one tell. No, x equal to exactly 1. Soumitra. So here, yeah. So this means exactly equal to 0, exactly equal to 1, and exactly equal to 2. So for x exactly equal to 1, we have two cases, this ht and th, where the number of tells are 1, and then x equal to 2, this is the case. So we have only one case. So now what is the probability of x taking 0? It is
1 by 4.
1 by 4. Probability of x taking 1, it is 2 by 4, and probability of x taking 2 is 1 by 4 again. So if you plot this, so this is my axis representing random variable values. This is x, and it can take 0, 1, 2. So if you plot these probabilities for x equal to 0, okay, let me have this y axis which represents probability. So it can be max 1. So let us divide this. This is 1 by 4. Fine. One by 4, 2 by 4, 3 by 4, and 4 by 4, that is 1. So for x equal to 0, we have the probability of 1 by 4. For x equal to 1, we have probability of 2 by 4, that is nothing but 1 by 2, and x equal to 2, it is again 1 by 4. So in this case, the nature of random variable x was discrete. It takes discrete values 0, 1, 2, and so on. And this distribution that you are getting, it is called as discrete probability distribution. Why discrete? Because the probabilities are discrete in nature, means the random variable is discrete in nature first of all, and we have probability associated with each of the discrete random variable. Hence the name discrete distribution, discrete probability distribution. For can anyone tell me any example of continuous random variable, like where the random variable can take continuous values?
Age, weight, height, sir.
Yeah. Thank you, Shravan. So yeah, say weight of the person. The random process is selecting any person from your town and measuring the exact weight of the person. So exact weight of the person can range from 0, that is a hypothetical case, like no weight, to infinity. Okay, so say I have 40 weight of 40 kg, but is it exactly 40 or 40.01 or 40.0001? You can take any precision. Okay, so we generally measure in discrete values like 40, 50, 60, 70, and so on. But within this two numbers, like between these two numbers 40 and 50, there are actually infinite numbers present over there. So we cannot like simply take 40 and 50, like quantize this. The weight can be between this as well, like weight can be 40.05 or 41.111 or so on, anything. So the exact weight can be anything between 0 and infinity, and hence the nature of this random variable, which is weight, is continuous in nature. Okay, so now how will you define now, like So in this case we were having a discrete probability distribution. So for random variable, for continuous random variable, we will have a continuous distribution, and one of the examples of continuous distribution is a normal distribution. Okay. So what it suggests is, say this is having mean mu. Okay, so can anyone tell, like in this case we were having this notion of probability for a particular random variable, exact value x equal to 1. Say I have a value here, some z. So what will be probability of z taking certain value x, or say 49? Anyone? Will it be yz? Will probability of z equal to 49 be yz? That is the question. And the nature of the distribution is continuous. Please think over it. Since it is continuous, there are infinite number of points. So will probability of z being equal to 49 be yz? So this is z over here, and it is having a value of yz on the curve. Anyone? In this case we were having like this. So this was the distribution. We were saying that probability of x equal to 2 was 1 by 4, which was the y-axis value. Here 2 by 4, and for x equal to 0 it was 1 by 4 again. So in the case of continuous distribution, will it be yz or something else? Just you can guess it, like. Okay, Samita says area under the curve. Okay, I'm asking, okay, area under the curve, fine. Thank you for bringing that point. So what will be the area under the curve for this one point? Yes, area under the curve is the right answer. For like area under the curve for continuous distribution, area under the curve corresponds to the probability. But what is the area under the curve for just one point? Like this one point, exact one point. 0, exactly. So in the case of continuous distribution, the probability of any random variable taking exact value is 0. In that case, so how we find the probability in the case of continuous distribution? It is nothing but the area under the curve. So that brings us to the question of point estimate and confidence interval. So we'll discuss that in detail. First of all, we were left with some topics, like some different types of distribution. So the way this distribution takes shape, it depends on the parameters of the distribution. So let us see different sorts of distribution. Let me just stop sharing. Okay, I hope my screen is visible. Anyone, can you please confirm? Okay, thank you, Ravi.
Yes, sir. Yes, sir.
Yeah. So let me go back over here. Yeah. So first of all, we saw. So as we discussed, there are two types of probability distributions: discrete distribution and continuous distribution. And in that discrete distribution, in this course, we are discussing three types of discrete distributions: binomial, Poisson, and hypergeometric, and in the case of continuous distribution, uniform, exponential and normal. So it depends on the problem at hand, like what kind of distribution you are going to assume, and also on the nature of the random variable. So what is a binomial distribution? So it's a distribution of like over fixed number of trials in which you want certain successes. For example, okay, let us go and see the binomial distribution formula. Okay, so last week we discussed about permutations and combinations. So I am doing n independent trials, and out of that I am assuming in I want to know the probability of successes in x trials out of this n trials. So say I am tossing coin n times, and I am saying probability of getting ahead is success, or getting ahead is success and getting a tail is failure. So in n trials or n times I am tossing a coin. Okay, let me just share it on the screen again. Say I am tossing a coin 20 times. In each toss I might get a head or a tail. What I am saying is probability of getting a head, which I am denoting as P, is success, assuming it is a unbiased coin. So probability of heads is equal to probability of tails. In case of biased coin, the probabilities might be different. So what will be the probability of tail? Say let us see it is not a unbiased coin. P can be anything between 0 and 1. So what will be probability of tails? 1 minus P, exactly. Because by definition of probability, the sum of all the events should be equal to 1. So there are only 2 events in this, elementary events, that is probability of getting a head or getting a tail. It should be 1. So probability of heads is P. So probability of tails will be 1 minus P. Okay. So what binomial distribution does, out of this n trials, say these are n, or let's say 20 for ease of understanding. Out of this 20 trials, what is the probability of getting like success in 10 or say 15 trials? So out of 20, I am taking getting success in 15 trials. So it will be P to the power 15, 1 minus P to the power 20 minus 15. So is everyone getting why this P to the power 15 and 1 minus P to the power 20 minus 15 is coming into picture? Any query on this, or is it clear? Adesh, are you having any query, or you want me to explain?
Sir, explain again, sir.
Okay. So in how many ways? Okay. So say I am doing one experiment in which I am getting heads 15 times continuously, followed by tails 5 times tails. Okay. So what will be the probability of this event? It will be probability of head getting ahead into probability of getting ahead into probability of getting ahead, and so on, into probability of getting a tails, and so on, right, by law of multiplication. Is that clear? These are independent events, right? So what we saw, probability of A intersection B is probability of A into probability of B in the case the events are independent. So in this case also all these events are independent. So it will be probability of head and head and head and so on. Let me just write it in tails and tails. So it will be probability of head into probability of head and so on. So how many times this heads are? 15 times, right? I am assuming like I want 15 successes. So this is 15. So it will be p to the power 15 and 1 minus p to the power 5. But now the question is, these heads, I am in the first thing I am assuming all these heads are consecutive.
So how we will get p to the power of 15, sir?
Because it is p into p into p into p 15 times. So
Okay,
p into p is p square, p into p into p is p cube. So p into p 15 times will be p to the power 15. Similarly, 1 minus p 5 times will be 1 minus p to the power 5. So now this is one arrangement of getting heads and tails. Another arrangement can be, let me erase this, heads, tails, heads, heads, heads and so on, and then followed by 4 tails. So one tail is coming over here, one tail is coming over here. So the number of trials is fixed. I am having 20 trials and I want to find the probability of getting success, 15 success. So out of 20 trial, I want 15 success. So what will be the probability of getting 15 successes in 20 trials? So in this case, in the first case it was h 15 times followed by 5 times tails. In this case it can be h, t, then followed by 14 times h and then 4 times t. So what will the probability again? P into 1 minus p into p and so on into 1 minus p into 1 minus p and so on. Is this clear for this kind of arrangement? Shavya?
yes, sir. Clear, sir.
Yeah. Please let me know, like if you don't understand, I'll explain it again. Okay. So this is one arrangement. Then I can also have h, h, t, h, and then followed by t, 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 and or h, 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 t, t. So there are multiple possibilities where these 5 failures can come and 15 successes can come. So now to get arrangement, what do we use? In last class we saw, to get different arrangements of items we use, anyone? Out of 20 elements I want 15 h. So what are the ways of arranging this?
Sample space.
No. What term, like what do we use for that? Combination, permutation?
Combination.
Yes. So out of 20 trials I want 15 successes. So the number of ways in which I can arrange this 15 successes is 20C50, and then the probability of each event. So in this case also, like no matter how you arrange, so 1 into, say let us say this example, 1 into 2 into 1 into 1 and 1 into 1 into 2 into 1, 1 into 1 into 1 into 2, all these are same, right? Only the arrangement where you are getting that 2 is different. So this product will be the same, p to the power 15, 1 minus p to the power 20 minus 15. So there are 20 trials, out of which in which 15 you are getting success and 20 minus 15, you are getting failures, that is 1 minus p. And you can make the arrangement in 2015 way, like this HHTH or HHHTTT and so on. So there, in generalizing this, you get for n trials, probability of getting r successes is NCR p to the power r 1 minus p to the power n minus r, where n is the number of trials and r is the number of successes. Okay. Is it clear, everyone? Okay, great. So this was binomial distribution. Now there are other concepts involved with binomial distributions. It will again take another course to discuss binomial distribution itself in detail, like the mean of the binomial distribution, like in probability, expected value. So there are two terms, expectation and variance. So for discrete random variables, we use this square bracket. Expectation is nothing but mean, and variance you all know, it's square of standard deviation. So for every distribution there will be mean and a variance. Yeah, sure, Nikhil, I'll talk about CDF, PDF, PMF and CMF.
Thank you.
Yeah. Okay. Fine. So to discuss this, it will take time. I'll just tell you, for this binomial distribution, the mean value or the expected value will be n into p, and the variance will be n into p into 1 minus p. This 1 minus p, which is probability of failure, is also denoted as q, and in literature you will find this notation, npq and np. So the mean of this is, so there is a derivation involved in this, so we won't be going into the detail, but you can remember this, that the expected value of binomial distribution is np, where n is the sample size and p is the probability of success, and for the variance will be n into p into q. Okay, fine. Now the next distribution is, what was it? Poisson and hypergeometric distribution. So can anyone tell what is the formula for Poisson distribution? There is a random variable x. So what is the and it is following Poisson distribution. So what will be the probability that the random variable x takes the value small x? Anyone?
Can you come again?
There is a random variable x and it takes a small value x. The random variable capital X is following Poisson distribution. So what will be the formula of Poisson distribution? For binomial distribution, it was ncx p to the power x 1 minus p to the power n minus x, where this p is known as the parameter of the distribution. Similarly, in the case of
Poisson of your lambda. No.
Yeah, so in the case of Poisson distribution, there is a parameter called lambda. So the formula for Poisson distribution is lambda to the power x upon x factorial into e to the power minus lambda. And what is the nature of this distribution? Is it continuous or discrete?
Discrete.
Yes. And you can see from here as well, x cannot take means x factorial is only defined for the continuous value, discrete values like 4 factorial, 2 factorial and so on. It cannot be like 4.12 factorial and so on. So by looking at this, even if you didn't know about this, like if it is a continuous or discrete, you can just look at the equation and see if it is a continuous or discrete in nature. Okay, so
Sir, a doubt, sir. So when you look at a problem, so how do you differentiate immediately that this belongs to that distribution or this can go with this?
yeah, so that is a good question. So it depends on, like say for example, like you have fixed number of trials and you want to find the probability of getting fixed number of successes in that.
Okay.
So in that case you will go for binomial distribution.
Binomial. Okay.
Yeah, but in the case of Poisson distribution, so why is Poisson distribution used? Okay, let me just show you the graph of plot of Poisson distribution. Let me stop the share over here. Okay, I hope my screen is visible.
Yes.
Yeah, so if you see the point, first of all, let us see binomial distribution once. Yeah, so it looks like this. It's pretty much similar to how the normal distribution looks, but one thing you should notice, it is discrete in nature. So you can see discrete points over here. It's not continuous in nature. So for every value of n or x random variable, you have certain probability associated, and sum of all these probabilities is 1. So depending on the value of p, the nature or the shape of the distribution changes. Like if you see p is 0.5 and the number of samples that you have is 20, so the distribution kind of looks like this. So it changes with the parameters like the p value and the sample size as well. Now let us see Poisson distribution. Okay, so you can see that the shape of this Poisson distribution also changes with the value of this parameter lambda, and lambda is nothing but an average computed over a longer duration. For example, we'll see one example of Poisson distribution in which okay, let us go to the example first so that it is clear to you like when to apply Poisson distribution. Let me see if the
Yeah,
example.
sir. Example wise, problem would be
Yeah. So let us see like in that example, I'll take that question and show you like it was belonging to Poisson distribution and not to the binomial distribution. Okay, just a quick question. Poisson probability distribution is which of the following type? So the answer we just discussed, it is discrete probability distribution. Fine. Assuming a binomial distribution with p equal to 0.5 and a sample size of 100, the expected value of this distribution is the mean value. What is the answer? We just discussed it.
Sir, 50, sir, answer.
Yes, so it is NE to P. P is 0.5 and the sample size is 100. So NP is the answer. Okay, and hypergeometric, we will discuss hypergeometric distribution. Okay, so this is the problem. On an average, 2.5 customers visit a departmental store each day. Find the probability that on a randomly selected day, the store will be visited by exactly 2 customers. Now, Nikhil, coming to your question, does it sound like a binomial distribution question? In binomial distribution, you will have
yeah.
fixed number of trials, right?
Yes. Yes.
Yeah.
Sir, B, sir, answer.
Uh, please wait for that. Like it is not that straightforward to answer these questions. So it's like okay, on an average, so the data is given. On an average, 2.5 customers visit the department store each day. The moment you see like this, there is an average given. It is highly probable that the problem or the distribution is Poisson distribution, and the value of this parameter lambda is given. So for example, 3
But
customers.
it isn't a discrete value, sir. You have told me 2.5 customers have
No,
visit.
this is the value of lambda, not the value of x.
Okay.
The random variable is the number of people visiting
Okay.
or the number of customers visiting.
Okay.
The lambda, it represents the average computed over longer duration. So on an average 2.5 customers visit the department each day. So it is 2.5 customers per day. So you'll have to note this, the other term, per day. 2.5 customers per day. It can be 2.5 customers per hour or 2.5 customers per minute and so on. So
That will be continuous, right?
yeah, so that will be continuous in nature, but the value that the random variable takes, in this case the random variable is the number of customers, and number of customers can never be continuous, right? It will be 0 customer, 1 customer, 2 customer and so on. So here first of all you will have to see what is the random variable. Random variable in this case is number of customers. In the case of Poisson distribution, random variable is discrete in nature, so it can be the number of customers or anything, but average value can be anything between like it can be floating point or like decimal point value. So is that clear, Nikhil?
Yes, sir. So how to approach this question actually?
Yeah, so now let me go back to my iPad. Okay, is my iPad screen visible?
Yeah.
Yeah, so the data that was given was lambda was 2.5 customers per day, and we were asked to find probability of exactly 2 customers visiting
Yes.
in that day. So question was what, let me just paste this question over here in chat. On an average 2.5 customers visit a department store each day. Find the probability that on a randomly selected day, so here randomly selected day, not randomly selected hour, so the unit should be matching, like whatever unit is there it should be same as what they are asking for. So randomly selected day, this what is the probability that on a randomly selected day the store will be visited by exactly 2 customers. So what is the probability of x equal to 2, where x is following Poisson distribution? It will be 2.5 raised to 2 upon 2 factorial e to the power minus 2.5, and the value of e is generally like what is the exact value of 2? It is 2 point something, right? Okay, let me see the precise value of 2. E, sorry, it's 2.718281. It's continuous actually, so we fix it to 2.71 or approximate it to 2.71. Okay, Nikhil, is that clear?
Yes.
Yeah. So now the question is what you asked, like continue CDF, PDF, and all that. Okay, let us discuss
Yeah.
that.
Just one doubt I have.
Mhm.
In predicting this 2 persons visiting there, some other factors will also be affecting the visiting, say rainy day or some sunny day
Yes,
or
yes,
cold day.
yes, sir. So it's like it
How
is
do,
computed over large number of days, and on an average, irrespective of the other conditions, there are 2.5 customers visiting every day.
so can we incorporate those conditions also or no?
Those conditions are hidden and those are ignored over here.
Okay.
Yeah. So the moment you are given this data, it's like irrespective of the condition, other conditions. So everything is getting averaged out, and whatever lambda value you are having, it's purely an average. Okay, there seems to be some issue in my iPad. Okay, please bear with me. Sorry for that. Is my screen visible?
Not yet.
Okay.
Yeah.
Yeah. So in the case of discrete probability distributions, you will have discrete probabilities. So this is known as probability mass function or PMF. In the case of continuous distribution, it is known as probability density function or PDF. Okay, so probability mass function, so it will have every random variable will have certain probability associated with it. But in the case of PDF, as we saw, we define probabilities in terms of area under the curve. So for that, sorry. So just a second. Say this random variables in the case of discrete probability distributions are 1, 2, 3, 4, 5, 6, 7, 8. So you will have probability of each value, right? And so on. But if you want to know what is the probability of x less than equal to 3, how will you find this out? Anyone? Any answer? What is the probability of x less than equal to 3 in this case? Say I am having these values p1, p2, p3 and so on up to p8, and summation pi, that is p1 plus p2 plus p3 up to p8 is 1. What is the probability of x less than equal to 3? Okay, so people are answering probability at 0, 1, 2 and 3. Yeah, exactly. Jayesh, you are right. So it is. So what are the possible values of random variables here? It is only x less than 3, it's 1, 2 and 3. So the probability of x taking values less than 3 will be probability of x equal to 1, probability of x equal to 2 and probability of x equal to 3. Now can someone tell me what is the probability of x greater than 3? Yeah, so it will be probability of x equal to 4 up to probability of x equal to 8, which can also be written as from this 1 minus probability of x less than equal to 3. Is that clear? Because sum of all these probabilities is 1. So 1 minus probability of x less than equal to 3 is probability of x greater than 3. Is this clear to everyone? Nikhil?
Yes.
Yes. So this particular thing less than equal to, this is known as cumulative distribution. In the case of continuous
So
function,
PMF and PDF are ideally the same.
so PMF is in case of discrete distributions, and PDF is in the case of continuous distributions.
So formula wise, do you think there's a difference?
There will be, because like a formula in the sense like every distribution will be having its own formula. Like for normal distribution, it is 1 over root 2 pi sigma square e to the power x minus mu square
Yes,
by
yeah.
2 sigma square. So this is the formula for normal density curve or normal distribution, where sigma is the standard deviation and mu is the mean of the distribution. So in this case, we were directly summing it up, the probabilities. But in this case, in the case of so if you want, so there is this random variable x. If you want to find probability of x less than, say small x, probability of x less than equal to x. So in this case, it will be area under the curve, which is this. But do you see this is continuous in nature? So instead of sum, there will be integral, which will be from minus infinity to x over this particular formula of normal distribution with mean mu and standard deviation or variance sigma square. Is it clear, Nikhil? So this is known as cumulative density function.
I see,
Size.
sir. Like, sorry, size. Okay.
Yeah.
So just trying to understand the difference between PMF and CDF.
This is just a
PDF.
matter of
Ah.
naming convention.
Ah.
So CDF in general, like it's like you can see it's a cumulative. So it's like cumulative frequency, right? In the case of mosaic curve, like we have this cumulative frequency. What is a cumulative frequency? So you have frequencies of certain things.
Yeah. Oh,
Yeah.
okay. We need to add everything,
Yeah,
right?
add
For
everything
cumulative.
before that.
Yeah. So, but if it is a PMF, it's a probability of specific value, right?
Specific
If my
value.
understanding correct.
Yeah, in that case, it will be probability of a specific value. So each thing is having a specific value, right?
Yeah. Correct.
Yeah.
Correct.
So
So
in the
the example would be right. X, for example, probability of x is equal to 3 is nothing but PMF, and then the probability of x greater than or equal to 3 is nothing but CDF. Is my understanding correct?
less than equal to 3 in general.
Yeah, less than. Okay. Yeah.
Yeah.
Okay.
Cumulative.
Thank you.
It's like cumulative. You are accumulating till that point.
Okay. Got it.
So whenever you see CDF, it's actually cumulative. So it's in the case of discrete, you simply sum it up, and in the case of continuous distribution, you take integral or integration till that point.
Harsh, can we see some examples regarding PDF, PMF, CDF,
Yeah,
and
sure. We have some
so that
examples.
it will be easy to apply those.
Yeah. We have some example. Let me just show, like quickly discuss the other types of distributions, and
Sure.
then we'll see some examples in Colab.
So other set of distributions is where you directly apply the formula, right?
Yeah. So in the case of like we had two distributions, discrete and continuous.
Okay.
So in discrete we have binomial, Poisson. By the way, it's Poisson and not Poisson, so we don't want to take Poisson in there. So it's Poisson and then hypergeometric. And in case of continuous, in this course we have, like, there are multiple discrete and continuous distributions, but in this course professor has discussed 3 discrete and 3 continuous. So in the case of continuous, the well known is normal or bell curve, which we'll be using quite extensively throughout the course. Then we have uniform
And exponential.
and exponential. So we saw binomial, we saw Poisson. So what is hypergeometric distribution? Now, what hypergeometric distribution? Say I have 6 doctors and 12 engineers. So in total I have 18 people. So out of these 18 people, I select some 5 people. So what is the probability of getting 2 doctors and 3 engineers. So there are 6 doctors and 12 engineers. Total people are 18. Out of this 18, I am randomly selecting 5 people. So what is the probability of getting in this 5 people, what is the probability of having 2 doctors and 3 engineers? So it is defined as, out of 5 I am having 2 doctors. Are you getting this? Sorry, out of first of all, is the question clear, everyone?
So can you repeat one more time?
Okay, I am having 6 doctors and 12 engineers.
Okay.
There are total 18 people. Okay, let me just go to an example online. Okay, let me just search for some example that will be intuitive. Yeah. So a deck of card contains 20 cards, 6 red cards and 14 black cards. Okay, so there are 20 cards in which 6 are red cards and 14 are black cards. So 5 cards are drawn randomly without replacement. So this you have to note carefully whenever there is this without replacement. In the case of binomial distribution, what we were having fixed number of trials, and we were trying to get certain number of success, probability of getting certain number of successes. Here we are replacing, so there was like replacement was happening over there. Again, okay, let me not just confuse you with all these terms. So we have 20 cards and we are taking 6, it is having 6 red cards and 14 black cards. In terms of doctors, engineers, we have 20 people, 6 are doctors, 14 are engineer. So 5 people are drawn randomly, or in this case 5 cards are drawn randomly. What is the probability that 4 red cards are drawn? So out of this 5, 4 are red and the other one is black. Okay, is the problem clear now, Nikhil?
Yes.
Yeah. So I had 20 people, out of which 6 were doctors, 14 were engineer, and 5 people were drawn randomly from this 20 people. What is the probability of having 4 doctors in these 5 people? So that is the thing. So I have 6 doctors or 6 red cards. Getting 4 red cards, the probability will be like the number of ways in which I can get it is 64, right?
Yeah.
Yeah. And out of 14, getting 1 black card will be 14C1.
14C1.
Yeah, so 64 into 14C1, and out of 20 to get 5, it will be
20C5.
20C5. So it is 64 of getting 4 red cards out of the 6 red cards, getting 1 black card out of the 14 black card, divided by getting 5 cards out of the 20 cards, irrespective of the color. So that is the probability distribution here of
Okay.
getting. Yeah, so K over here is the success. Here success is defined as getting red card. So in general, if you see the formula, x equal to K, it will be KCK. Capital K is the number of red cards and K is the number of red cards you are getting in the sample. N minus K is, N is the total number of cards, which is 20. So N minus red cards will be the number of black cards, which is 14. So K is 4, it was 4 over here, and N minus K, N is the total number of cards you are drawing. So 5 cards were drawn. So N minus K will be 1 and 5 minus 4 will be 1. And this is total number of cards out of which you are drawing a sample of N. So out of total red cards, you are taking K red cards. Out of total N minus K black cards, you are taking small n minus K black cards. And so if you sum this up, it will be n, k plus n minus k is n, and small k plus small n minus k is small n. So it is like total number of cards and total number of cards drawn. Is this formula clear, everyone? You can say yes, no.
Yeah.
Okay.
So there will be 4 entities.
So there will be like 3 parameters generally, like the total number of points. Yeah, so means 4 in the sense like total number of data points, and the sample size, and the success. It is given to you that the number of different like number in each of the groups, like red cards and black cards is also given. So even if you are given just the number of red cards, you can just find the number of black cards by just subtracting it from the total number of cards.
So how do you get the 1 actually? 14 black cards.
Yeah.
5 cards are drawn randomly without
Yeah,
replacement.
and then they are asking exactly 4 red cards.
Oh, okay.
So the other one should be black card. Is it clear?
Yeah, sure. Can we see another example?
Another example. Okay, let us see another example. Okay, everyone please be on mute. Okay, so here is an example. In a class consisting of 45 boys and 15 girls, 10 students are selected one by one. What is the probability of finding 4 girls? So here, how will you approach is total number of students will be 45 plus 15. So capital N is 60. Is that clear?
Yes.
Yeah. Here, what is the probability of finding 4 girls? So here, getting finding a girl, we are terming it as a success. So here k is 15, that is total number of girls,
Okay.
and the sample size is 10. Okay, and you want to have small k equal to 4. So it will be, let me go back to iPad. Okay, let me paste this question in chat. Okay, so the question says there is a class in which there are 45 boys and 15 girls. Out of this, everyone please be on mute. Out of this, 10 people are selected. So what is the probability that in this 10 people, 4 are girls? So which means the rest are boys. Is the problem clear now?
Yes, sir.
Yeah. So capital N is the total number of people, which is 45 plus 15, which is 60. Small n is the size of the sample, which is 10. Here capital K, the thing that is asked in this question is probability of getting exactly 4 girls. So the capital K will be 15. So the probability of, forget about these notations, probability of getting like the number of ways in which you can get 4 girls out of 15 girls is 15C4 into the remaining ones. Out of 45 boys, you can get 6 boys is 45C6, C6, and total number of ways in which you can get 10 people is 60C10, right? Is it clear? Nikhil, Shivakumar.
Yes.
Yeah. So this is nothing but k over here. Out of k, this is small k. These notations, by the way, are not universal for hypergeometric distribution. Every place you might find some different sort of notations. So this capital K is the total number of favorable cases, out of which you are getting k successes, and then the rest of will be capital N minus k, capital K, which will be the number of boys, out of which you are getting small n minus k boys, and in total you have n, and out of which you are taking a sample size of n, small n. So I hope this is clear. And then this distribution where like a random variable takes a value of k is the nature of this distribution is the distribution is called hypergeometric distribution. It comes from the name of geometric distribution. It is not taught actually in this class. There is a distribution called as geometric distribution, in which you get success out of n trials, you get success at the last. So let us not discuss that and get confused, but yeah, this is hypergeometric distribution, in which you have two groups, and then you are drawing a sample of size n. One group is favorable one, and you like in this case it was girls. You are getting small k value of like what you want to find what is the probability of getting the small k number of girls from the k girls. So the random variable can take values 0, 1, 2, 3 up to capital K. Is it clear, everyone? Let us see another example. Let me put this in chat.
Just one doubt. These names are derived with the equations which this curve is following. Is it that?
In the case of normal distribution, yes. The way it is, the way this formula is, that will define the nature of the curve, how the curve looks.
Nature means that is the equation of the curve.
The shape of the curve. Equation is there.
Okay.
That will define the shape of the curve.
Okay.
Yeah. So if you, in the case of normal distribution, root 2 pi sigma square e to the power minus x minus mu square upon 2 sigma square. So it generally looks like this, where this is the mean center, and you have standard deviation, which shows the dispersion of the distribution or the data. So if mu is high, so in this case, say the normal distribution, standard normal distribution is having mean 0 and standard deviation of 1. Now if the mean is 5, so this mean, the distribution will shift over here, and let's say standard deviation is still 1. This is the case, the mean has shifted by 5. Now if the mean is 5 and standard deviation is 2, it means that the spread of the data is high. So the distribution will look like this. Here sigma is equal to 2, say. So depending on the value of these parameters, the shape of the distribution will change. Does that answer your query, Akhilesh ji?
Yeah.
Yeah.
Okay.
So the formula is there, and it has certain like a function that this particular expression is having certain distribution, like a curve which you can draw, and the shape of the curve will change based on the parameter values. Similarly, in the case of binomial distribution, as we saw earlier, okay. So the shape of the binomial distribution was changing based on the value of p and n. Similarly, the shape of the Poisson distribution will change based on the value of lambda, and let us say hypergeometric distribution, how it looks. So you can see that it is pretty much looking like a normal distribution, but it is not a normal distribution. Again, it is a discrete distribution. So you can see, depending on the value of n, the total number of people, the favorable number of people, and the sample size. So the shape of this particular distribution will also change, and the formula was kck n minus k c n small n minus small k and ncn, and the random variable x is taking the value of k over here. So that determines the shape of this distribution, and it may not be like that. If you see over here, it changes also. This this is PMF and this is CDF. So CDF is as we discussed, it will be like summation till that particular point, and as you approach to the end, it will become 1. Is that clear to everyone?
Right.
Okay, so these were the three discrete distribution, binomial, Poisson and hypergeometric, and we were supposed to discuss some examples. Okay, let us quickly see one and then we'll go to Colab and solve some problems over there. And there are other distributions, uniform and exponential. I'll quickly tell you what these distributions are and we'll proceed. Okay, a quiz team is to be chosen randomly from 15 boys and 12 girls. The team has 7 slots. The goal is to find the probability that 4 of the players will be girls. Here, okay. Let me just paste this thing, and I ask everyone, like, what will be the value of n, capital N, capital K, small k, and small n. Can anyone tell? I have put the question in chat, the part of question. So there are 15 boys, 12 girls. Okay, so goal is to find the probability that 4 of the players will be girls. So capital K will be total number of girls. Yeah, that is correct, Soumitra. What is capital N? Okay, small k is 4, fine. Capital N? Yes, it is 27, that is 15 plus 12, total number of people. What is small n? Okay, small n, it's not very clear. Yeah, it's given over there in the in some other name. Yeah, it's actually 7. So they are taking 7 people out of that. It's not very clear. The team has 7 slots. They mean that 7 people will be taken. Yeah. So all these things are there now with you. You have capital K, you have capital N, and you have small k. So you can find out the probability of x equal to small k. It's capital K C K into capital N minus capital K C small n minus small k divided by capital N C small n. So you have 3 parameters over here, capital K, small k, and capital N. 4, capital K, small k, capital. Parameters are 3, capital K, capital N, and small n. And k is the random variable value, small k. Is that clear to everyone? Nikhil? Okay, let us see one more example. In a basket consisting of 20 apples and 15 oranges, what is the probability of selecting 5 oranges after drawing 10 fruit from the basket? So here capital N will be, okay, there is a mistake. It should be 35, not 36. There is a mistake over here. Capital K is 15 and small n is 10. In this case, in a foreign university comprising of 1000 students, out of which 350 are of Indian origin, what is the probability of selecting 5 Indians when 20 students are selected? So 20 students are selected, small n is 20 and capital K is 350, small k is 5 and capital N is 1000. Okay, any query? You look into more and more examples of hypergeometric distribution, you will get a clarity on this. So this is just one source, you will find multiple such sources over online. So you can look into more such problems on binomial distribution, Poisson distribution and hypergeometric distribution and normal distribution. And then there were two other types of distributions, out of which a continuous distribution, one was uniform distribution. As its name suggests, uniform distribution. So between two values A and B, you are having uniform probability. So all the values between A and B are equiprobable, and outside of that its probability is 0. So this kind of distribution is called as uniform distribution. So at every point the value of this particular curve will be 1 upon B minus A. How it is coming 1 upon B minus A? Okay, area of this curve will be 1 by the definition of probability, right? And say height is h, so it will be h into B minus A, that is area of rectangle, equal to 1. So h equal to 1 upon B minus A. Is that clear? Is it clear like why that value is 1 upon B minus A?
Yeah.
Yeah. So the area of this curve will be 1. So it is nothing but area of this rectangle, and the length of this is B minus A, and this is h. So h into B minus A is 1. So h equal to 1 upon B minus A. So that's why this particular. Okay. Similarly, for all the probability distributions, density curve, the area under the curve will be 1. In case of discrete probability distribution, the sum of all the probabilities will be 1. Okay, so this was uniform distribution, and then we have exponential distribution. As its name suggests, it's exponentially decays with higher values of random variable depending on the parameter lambda, which is, or they also use it as mu in literature. So you might find, like in the case of Poisson distribution also, you might see like people using different symbols for the lambda. So yeah, just take care of that. It's the same thing, it can be either lambda or mu, but the distribution is exponential distribution in this case. In the case of Poisson distribution, it was lambda to the power x upon x factorial e to the power minus lambda. In the case of exponential distribution, it is 1 by mu or 1 by lambda e to the power minus 1 by lambda x, and it is continuous in nature. So yeah, you can always visit like Wikipedia and see like the cumulative distribution function as well for each of the distribution, like for exponential, uniform and other distributions as well. Okay, I hope this different types of distributions is clear. Now we'll go on to some problems and solve them using Colab, like Python. Okay, so in this case, on an average 2.5 customers visit a department store each day. Find the probability that on a randomly selected day, the store will be visited by exactly 2 customers. So it was a Poisson distribution, and random variable was the number of customers. Okay. So answer, we'll do this in collab as well. Okay. So what will be the case over here? Like answer I am displaying. So the store will be visited by at most two customers. We just discussed this, right? Let me put this in chat again. On an average, 2.5 customers visit a department store each day. Find the probability that on a randomly selected day, the store will be visited by at most 2 people. Okay, so definition of at most.
Minimum 2 people.
No, at most 2 people. It's not at least. So there are different. At most,
Okay.
at least, less than, and greater than. So at most is
maximum to minimum,
less than equal to, and at least is greater than equal to. So probability of X getting number of 2 customers visiting in a day, this is exactly 2 customers. At most 2 customers will be less than equal to 2, at least 2 customers will be greater than equal to 2, and less than 2 customer strictly less than 2, and greater than strictly greater than 2. Sorry. Yeah, so please keep this terms in mind. At most is less than equal to, at least is greater than equal to, less than, and greater than. Okay, so now coming back to the question. On an average, lambda is given 2.5 customers per day. Find the probability that on a randomly selected day, the store will be visited by at most 2 customers. So what will be the value? The number of customers can be. So what all values can this particular random variable take? Number of customers.
0, 1 and 2.
No, in general, what all values this X can take? That is number of customers. It can be 0, 1, 2, 3 and so on till infinity, right? Like infinite number of customers can visit me.
Yes.
Yeah. So in this case, P of X less than equal to 2 will be P of X equal to 0, P of X equal to 1 plus P of X equal to 2, which is nothing but substituting in the formula. So what is P of X equal to small x, lambda to the power x, x factorial e to the power minus lambda. So it will be, you can substitute lambda later. Okay, let me just substitute lambda directly. 2.5 to the power 0 upon 0 factorial e to the power minus 2.5 plus 2.5 to the power 1 upon 1 factorial e to the power minus 2.5 plus 2.5 to the power 2 upon 2 factorial e to the power minus 2.5. So if you solve this, you will get the answer. Similarly, in the second question, in the next question, it is asked the store will be visited by at least 2 customers. So in that case, it will be X greater than equal to 2. At least 2 customers. So now this is impossible to find, right? Like you cannot just simply sum P of X equal to 2 because there can be infinite number of customers, right? And so on. So what will you do? By the definition of probability, you know.
1 minus probability
One
of
minus.
X less than
Yeah.
equal to 2.
So 1 minus probability of X less than strictly less than 2. it will be 1 minus p of x equal to 0 plus p of x equal to 1. Now you can find these two things. So you'll have to approach these problems like that. Okay. Now let us see like what all is left in this, then we'll go to Colab. So okay, so at least 2, answer is 0.71. Okay, a basket contains 10 rotten tomatoes. One. Okay, this is a probability question. I'll leave it to you. Like there are 2 questions in this, so these are just for your practice. So I'm not going into those problems. Okay, a survey found that 65% of the financial consumers. Okay, I hope my screen is visible.
Yes, it's visible.
Yeah. A survey found that 65% of all financial consumers were very satisfied with their primary financial institution. Suppose that 25 financial consumers are sampled, and if the survey results still holds true today, what is the probability that exactly 19 are very satisfied with their primary financial institutions? Okay, so what kind of distribution is there in this case? Anyone? What distribution is being should be used over here? You have been given that 65% of all financial consumers were very satisfied, and you take a sample of 25.
Binomial will be used, sir.
Okay, what about others? Let me put this question in chat as well for others. A survey found that 65% of all financial consumers were very satisfied with the primary financial institutions. So you are taking a sample of 25 samples, and out of which you are asking like what is the probability that exactly, you will have to notice this, exactly 19 are very satisfied with their primary financial institution. So what kind of distribution is being followed over here, or should be used? Okay, Poisson, but why Poisson? It's not Poisson. In case of Poisson, you will be having an average, right? So is any sort of an average given over here?
65%. Is the average?
Is that an average? So in the case of Poisson distribution, the average will be having a unit something per time unit. So like 2.5 customers per day, or 4 liters per hour, like that. So the average will always be given like over certain duration. So like if a school is being visited by some students, so like
So in a fixed time scale.
sorry,
In a fixed time scale.
yeah, in a fixed time scale, yeah. So that is the case of Poisson distribution, but this is not, there is nothing given as such over here. So what will be the distribution? Somebody answered earlier.
Just one thing. Our previous question, 2.5 customers were visiting.
2.5 customers per
That
day.
was not.
Yeah, it was 2.5 customers per day. So the random variable was number of customers visiting in a day. We'll see that kind of an example in Colab as well.
Fine.
Yeah. So there is no such information over here. Again, is it a hypergeometric distribution? No, because you are
Binomial.
yeah. So it's not like hypergeometric either. Like you have not been given 2 groups, like girls, boys, and so on. So it's not hypergeometric. So the one distribution that should come to your mind is binomial distribution. So let me share my iPad screen. So here 65% of customers or consumers were very satisfied. So the probability of success is 0.65. They are taking a sample of size 25 and they are asking exactly, so what is the probability that exactly 19 customers are satisfied? So it will be out of 25 you are taking 19 customers and 19 of them are satisfied and the rest 6 customers are not satisfied. So this is the answer. Is it clear, everyone? So you'll have to see the data, like how what is the data given. Based on that you'll have to identify the distribution, and you can cancel out certain things like is it Poisson, like is there any lambda given? No. So Poisson distribution is ruled out. Is it hypergeometric? No, because there are the two groups are not given, boys, girls, or apple, oranges, or anything. So the left one is binomial distribution, because here again you will have to see the nature of the random variable. Here the random variable is number of consumers, so it is discrete in nature, so it should be discrete distribution, and in that Poisson and hypergeometric distributions are ruled out, so the left one is only binomial distribution. Fine, let us go back. So now we will solve all these things in Python. So before that I have also shared this one notebook. This was supposed to be covered in the week 2, like finding the mean statistics, descriptive statistics of the given data. So there is this data list containing data points, and then you can find the mean, median, mode, standard deviation, like the sample standard deviation, population standard deviation, and so on, and sample variance, population variance, and all these things like interquartile range, and the percentile, like 25th percentile or the quartiles. So I have given this code, like this is using the statistics library, this is using NumPy and SciPy libraries, and the first one is here using pandas library. So you can use any of the libraries, whatever suits you the most. Yeah, so you can take a look at this. This is uploaded in week 3 mostly, like in the week 3 folder. So just have a look at this. For those of you who do not know, like I'll be uploading all this material to my YouTube channel. Oops, sorry. Sorry everyone, I got disconnected. Hello everyone, sorry I got disconnected. Can someone mention like where I got disconnected?
Yeah, I mentioned I already.
At what point did I get disconnected?
You were showing that library. Yeah,
Yeah.
this one.
Okay,
Yeah.
thanks. Yeah, so I have created this notebook in which like you can find all these descriptive statistics like mean, median, mode, and other things using pandas library or using NumPy statistics library, or simply using NumPy and SciPy libraries. So please have a look at it, and you can also refer to the online documentation if you have any queries. You want me to zoom? Okay. Yeah. Fine. So I'm not discussing this. This is just for your reference, like how to find mean, mode, median, standard deviation, and all these descriptive statistics of the data given to you in the form of list. So you can have a look at it. Let me now go to another notebook. Yeah, so here are the 6 distributions and how to use them in Python. So first of all, binomial distribution. So there is a library called SciPy in which there is a submodule called stats. From that we are importing this distribution binom. Similarly, in SciPy stats we have Poisson, hypergeometric is known as hypergeo, and uniform, norm, and exponential expon. So from SciPy I'm importing for SciPy.stats I'm importing binom, and I'm given n, p is the parameter, n is the number of trials. So the PMF or the probability mass function will be binom.pmf. There is a function in this submodule binom.pmf, probability of getting 5 successes and total number of trials n, and the probability value p, that is probability of success. So this way you will get, let me just run this. Okay, it is connecting. It will take a minute. Yeah, so probability like binomial PMF for 5 successes, that is exactly getting 5 successes in the 10 trials with 0.5 probability of success is 0.24, and CDF is nothing but less than equal to 5, like cumulative distribution function, the probability of x less than equal to 5. Okay, and you can change this parameter values like n number of let me just change the value over here, 65. So you will see the values over here also got changed accordingly. Similarly for other functions as well, Poisson distribution, the parameter is lambda, and here Poisson PMF for 2 events. So we'll see some example in which like there will be a real life examples. This is just for the syntax of this, like how to use this particular thing. So PMF CMF is given for all the distribution types. Similarly, uniform A and B values are given, then mu and sigma, that is mean and the standard deviation for normal distribution, and exponential lambda inverse. So yeah, you'll have to like 1 by lambda is lambda inverse actually. So generally they give it in terms of 1 by lambda because the distribution is like 1 by lambda e to the power minus 1 by lambda and so on. So the value that you are giving as input over here is 1 by lambda. So we'll come across some examples and then we'll look for the applications of this. So here are the problems. I hope it is readable and my screen is visible, everyone.
Yes, it's visible.
Okay, thanks. So again, this is in week 3 problems. This was in week 2 statistics, but it is uploaded to week 3 week 3 folder in only. Okay, I was telling, like, for those who do not know, I have this YouTube channel where I'll be uploading the recordings of these sessions, and you can go to the recording, and in the description you will find a link over here. This link will redirect you to a folder in which all the material covered in this course is like in this sessions is being uploaded. So you will find the week 2 data over here and so on. This is data analytics with Python, sorry, the other course that I took last time, last semester. Sorry, the joy of computing is what I took last semester. So in this case you will find over here, like in the week 3 content, all these 3 notebooks are there. Is it clear to everyone? I'll just share the link to my YouTube channel again over here for the sake of those who are joining for the first time. Yeah. So going to the problems. So I'm importing SciPy, which is because SciPy is having all these modules, statistics and all. Okay. From SciPy.stats, I'm importing binomial. So this question we saw in slides. A survey found that 65% of financial consumers were very satisfied with their primary financial institutions, and so on, blah blah blah. So what is the probability that exactly 9 are very satisfied? So here k is nothing but the number of successes, n is the total number of like the sample size, and p is the probability value, which is 0.65 in this case. So you can just simply run this. This is the value, and if you go over here, so 0.091 is 0.0 approximately 0.091. By the way, this is optional, like to give k, n and so on. You can also write it like as, just a second. You can simply pass on the parameters like this, 1925.65. It will still give the same output. Is it clear to everyone? Anyone?
Yeah, it's okay.
Yeah. Please unmute and answer, because I'll have to like go back and check the chat. Fine. So next problem. According to the US Census Bureau, approximately 6% of the workers in Jackson, Mississippi are unemployed. In conducting a random telephone survey in Jackson, what is the probability of getting 2 or fewer unemployed workers in a sample of 20? Again, this is a binomial distribution, and it is given 2 or fewer, or at most 2. Like language might change, but it is at most 2, getting 2 or fewer. So it is nothing but, let me just write it over here, probability of x less than equal to 2, which will be probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2. Okay, so this is like you are summing up the PMF over here, PMFs, like for every individual random variable value. So it can be probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2. Let me run this. It is 0.88. Instead of this, you can also use binom.cdf, which is less than equal to 2. It will do the same job as this. Okay, is it clear to everyone?
Yes, it's clear.
Yes, sir.
Yeah, thank you. So PMF is like exact that value, and CDF is like less than equal to that value. And if you want to find greater than 2 unemployed workers, so how will you do that? Probability of getting greater than like more than 2 unemployed workers.
It's 1 minus, right? 1 minus.
1 minus
Yeah, so it will be 1
CDF.
minus binom.cdf and whatever these parameters are. So this is greater than 2. If it were asked like at least 2, so it will be greater than 1, and so on. So you'll have to keep this in mind. Okay, coming to Poisson distribution. So here is a real world example. Suppose bank customers arrive randomly on weekday afternoons, on an average of 3.2 customers every 4 minutes. So now you'll have to notice this, on an average of 3.2 customers every 4 minutes, or 3.2 customers per minute. Akhilesh ji, is it clear now, like how the data is given in the case of Poisson distribution?
Right.
Yeah. So what is the probability of exactly 5 customers arriving in a 4-minute interval? Now the random variable is the number of customers arriving, and you should notice this, this is 4 minute. They are giving the same time duration over here and here. So what is the probability of exactly 5 customers arriving in 4-minute duration on the weekday? So it will be probability mass function of Poisson, which is x to the power lambda to the power x upon x factorial e to the power minus lambda, and that's what it computes. So x is 5 here, small x, and 3.2 is the value of lambda. So if you compute this, oops, sorry, I have to run this first. It will be 0.11. Now, interesting part. Again, like this is cumulative thing. So a bank customers arrive, same question, what is the probability of more than 7 customers in a 4-minute interval? So more than 7 customers will be x greater than 7, which is equal to 1 minus x less than equal to 7, which is 1 minus x equal to 0, and so on. So you can use this CDF over here. So I have just assigned it to a variable, but you can simply write it like this: 1 minus.
So how do you know like which values to enter between the 7 and 3.2?
Yeah, so 7 is what? Okay, so greater than 7. What is cumulative distribution? It is x less than equal to that particular value.
Okay.
Yeah, so it is less than equal to this particular value. So if it is greater than 6, so it will be 1 minus x less than equal to 6. Oh, okay, and suppose if it is greater than equal to 7, so it will be 1 minus p of x less than equal to 6. Is that clear?
Yes.
If it were like probability of, okay, let me just copy this. So it depends on this. So it is greater than equal to 7, so it will be less than equal to 6. And if it is strictly greater than 7, so it means 7 is excluded over there, you will have to include 7 over here. Fine, I hope this is clear. So since it is like the random variable can take infinite values like 0, 1, 2, 3, 4, infinite number of customers can visit. So it is not possible to sum till infinity. So in that case, we just do 1 minus by using the definition of probability. All the sum of all the values will be 1. So it is 1 minus probability of summation till that particular point. So in this case, it is 1 minus Poisson or CDF 7 and 3.2. Now this is interesting. Okay, a bank has an average random arrival rate of 3.2 customers every 4 minutes. This is given. So lambda is 3.2 customers every 4 minutes, 3.2 per 4 minutes. What is the probability of getting exactly 10 customers during an 8-minute interval? Now, do you see a problem over here?
The interval is different actually, so we will have to either multiply.
Yes,
or
exactly. So we cannot do over here. So it is like this is the random variable value, 10 customers.
So this is again Poisson, right?
Yeah, it is again Poisson, but you will have to notice the lambda value is 3.2 customers per 4 minutes.
So we can say it as 6.4 per read,
exactly,
right?
that's what we have to do over here. So you have to make sure that this interval and this interval is the same. So 10 customers in it. Okay, Akhilesh, you have in doubt?
Yeah. Can we do other way around? 5 customers in
No,
4 minutes?
that we don't know. We don't know like 5 customers were arriving in 4 minutes. So in overall 8 minutes, 10 customers were arriving.
Okay.
Yeah. So here this is an average, 3.2 customers every 4 minutes. So you can multiply this by 2. So it is 6.4 in this case. Lambda will be 6.4. So depending on this duration, you will have to adjust the value of lambda. Like if it were 16 minutes, so then you will have to multiply this 3.2 by 4 and so on. So 10 customers, 6.4 customers per 8 minutes. So the value will be 0.05. Okay. Then there are some examples of uniform distribution and other things. So I'll urge you all to look into these things later, like at your own pace. like there is an example of every distribution added over here, so please look into it. We will now move on to other topics in this. So only 15 minutes are left, so I'll just touch upon these topics. The very important topic in this course, which is hypothesis testing. Okay, let me see if we have covered everything. Yeah, first of all, like point estimate and confidence interval. So what is a point estimate? Can anyone tell? Like I have a data, like I have a population, and population need not be like any physical physical entity in the sense like the exact the people only. Population, it refers to all the individual items into consideration. So my population is all the milk bottles in manufactured by factory. So every milk bottle is having certain amount of milk, and I want to take a sample. So we saw this sampling in the last session, like what is sampling and what are the different types of sampling. So I want to take a sample of say 10 bottles and infer about the population parameters, that is the population mean, that is the mean average amount of milk that is present in all the bottles, because I cannot go and check each and every bottle and measure that. So I just take a sample and infer something about the population. So this inferring something about the population from the sample statistics is known as inferential statistics, and descriptive statistics is nothing but like finding this mean, median, mode from the given data. But inferring something about the population from sample statistics is known as inferential statistics, and in that in this case we will be dealing with different sorts of problems. So can anyone tell, like, okay, there is a property. Okay, let me explain it to you on iPad. Is my iPad screen visible?
Yes, sir.
Yeah.
Yes, sir.
Okay. So say I have like multiple data points. So the actual population mean will be around over here. So I take random sampling. I do random sampling and take few samples. Say this point, this point. So what will be the mean? Where will the average lie? Approximately? Somewhere over here, right?
Yes.
Yeah. For this sample S1. Say I take another sample, this yellow dots.
Same as the global mean.
Around this point. Now say I take this points. This is sample 2, sample 3. What will be the mean? Where will the mean lie? Somewhere over here, right?
Right.
Yeah. So if you see the mean of the sample is changing drastically with respect to this population mean. So you cannot simply just take one particular mean and infer something like one sample of very small size. So as we discussed, outliers will have their effect. So here in this case I took the samples which were closer to the actual parameter, so hence the estimate was pretty correct. But in this case all were outliers in the sense they were far apart. So if you find the mean of this and infer that, okay, this is something mu dash, so this mu dash and mu are having quite a lot of difference. So yeah, so this is the problem. So you'll have to take samples very like properly, and like you cannot simply take anything like so. Okay, so what is our end goal? So our end goal is to find out this population parameter or estimate something about the population. So to get that, we'll have to, what is the way, like can anyone suggest like how to get a better estimate of the population parameter? Here I was taking a sample size of 4.
We can increase the number of samples.
Exactly. So if we increase the number of samples, so the chances are that like as more and more samples we take, the estimate will be closer to the population parameter. That is what our hypothesis is. But still, like there can be certain deviation, like it cannot be exactly the same. So whatever we are estimating over here, so this rate thing, this is called as point estimate. So we have an estimator which is taking samples and then estimating the value. So this is the point, these all are point estimates, and the difference between this point, each of this point estimate and the original parameter, this is called as bias. So this length is a bias for this is for bias for this, and this is the bias for this particular estimate. So now to take into account this variability, we take confidence interval into consideration. So what is confidence interval? It is nothing but an interval. So I say that my mean, so this is the point estimate, and my mean can lie somewhere between this interval. So you
I think he's again disconnected.
sorry, I got disconnected again. Is my screen visible?
Yes, it's
Yes.
visible.
Oh yeah, sorry for that. So we were having point estimate, and what we are saying, we need some confidence interval. So we say that we are X% confidence that the mean will lie within this range, like whatever our estimate of mean minus something, sorry, plus something and minus something. So the original population mean will lie something between and this thing over here is generally taken as standard error. Okay, so to get a better estimate, like we are saying that we are some X% confident that our population mean will lie between this range. So X bar is the sample statistic. In one of the lectures we were having this discussion, what is the mean, like how is the mean denoted. Professor Ramesh has used this M to denote the sample mean, but yeah, somebody rightly pointed out X bar is also used, and in further lectures or sessions we will be sticking to this particular notation X bar for sample statistic or for sample mean. So since the point estimate can be incorrect, so we are having this notion of confidence interval, where we are saying that we are some X% confident that the mean will lie between certain interval. So now this was all about the point estimate and confidence interval. Let me stop it over here. Okay. Again, now you had taking this means, right? This was one mean. This particular thing was one point estimate. This again point estimate, and so on. So if you take 1000 such different samples and compute the plot the distribution of this values. So the more and more number of samples you take, you will see that these means the distribution of sample means, it will again be a normal distribution. So just to demonstrate this, let me just go back to my laptop. So there is this nice website, onlinestatbook.com, in which you can do this sampling distribution experiments. I hope it is visible.
Yes, it's visible.
Yeah. So this is my original distribution. It can be anything. It can be uniform or normal or anything. What I am doing is, I am taking a sample and finding the mean. I take another sample, find the mean, another sample, find a mean, and so on. And let me just take 10,000, okay, 5 such samples. So these are the means of 5 such samples. Means this, for the mean is lying over here, like whatever means are lying, it is creating a histogram sort of thing. Okay, so let me just keep adding. So let me add 5 samples, like this is like for 10,000 samples. So I am taking 10,000 samples and so on. So this is the distribution of the means of the samples. So I am just keep on adding 10,000 samples to it. So do you see the distribution of the the sample means? So I was taking a sample and taking mean of it and then putting it over here. So the distribution of the sample mean is also a normal distribution. Doesn't matter if it is a uniform distribution. Let me do the same thing. Mean, so just to save time, I am taking 1000 such samples. So this is like one sample taken at a time. I am taking 1000 samples or 1 lakh samples. So do you see the distribution of the mean of the samples from normal distribution or any sort of distribution in general tends to a normal distribution. And if you see the mean of this distribution, you will see the mean of this distribution 15.99. It's closer to the sample exact the original distribution mean. But here the size of the sample size was 5. You can also try changing sample size. So animate. See, this is 2 sample and so on. Let me take 1000. Do you see the change in the shape of the distribution? And also the mean of this distribution. Again it is closer, like the more number of samples you take, it will be closer to it. Let me just clear this up. Let us take only 5 such samples, and if you see the mean of this, it is 10.94 and the original mean is 16, which is pretty far. And if I take 10,000 samples, you see that the mean is getting closer to the original distribution's mean. So even if your sample size is low, if you take more number of samples, your estimate will be closer. Okay, there is any query? Yeah, I'll share the link here. Yeah, just a second, Nikhil. I'll share the link. So here you can see that the estimate is closer to the original distribution if I take more number of samples. And in the case like, okay, let me just take it again. If I increase the sample size itself, you can see that with fewer number of samples, I am getting closer to the population mean. So I just took 5 samples from here, but the sample size was higher, so I was closer. So let me just take 10,000 samples. So you can see it is pretty much closer to the population mean. So this distribution of the means of samples will always be normal for most of the distributions. Like these samples were taken from uniform distribution. Even if you take it from skew distribution, let me just animate like take 10,000 from here, it is again normal, with the mean of this normal distribution closer to the actual mean. of the population, and so on. So this was about the mean distribution of sample means. So similarly, distribution of sample proportions will also be following. So if you take certain items from here and find the proportion of it, there is an example, we'll see it later. So the distribution of the sample proportion will also be following a normal distribution, with the mean of that particular distribution closer to the population, like the mean of the proportion of that will be closer to the population proportion mean. Okay, so yeah, this was about population and proportion and mean. And if you take the variance, of the samples and plot the variance of the sample distribution, so that will follow a different type of distribution called as chi-square distribution. So we'll discuss that in detail in the next class probably. It's already 8. So it was about distributions of sample mean, proportion and variance, and point estimate and confidence interval. So in the next class, it was supposed to be discussed now, but we will discuss it later. Apologies again, like we are running 1 week late for all the sessions. So but anytime you feel any doubt, please like look for the concept online, either on YouTube or other sources, and try to get those clarified. Like don't be very dependent on the material shared by NPTEL or these live sessions. You can always look into the topics online, the concepts online, and there will be a number of video lectures available from multiple authentic sources like Khan Academy and 3 Blue 1 Brown and multiple other sources. So yeah, but anyway, we will be covering these topics in our sessions, but just in case you feel like you are not getting anything, so please feel free to search online and get that clarified. Okay, so any queries so far in today's session?
Yeah, I have a question related to the confidence interval. See, there's one question in the week 4 assignment.
I can't discuss the question,
Yeah, you
that
can't.
directly, but yeah,
Yeah,
maybe we can discuss the concept.
even I will be discussing indirectly only because I think there's the correct option is not there in sixth question. Actually, the error this thing.
Okay, so maybe like yeah, let us not discuss it. Like, so probably if you feel that the correct option is not there, so and there is a mistake, so there are chances, like it happened earlier as well in NPTEL assignments, that there might be some mistake, so they will correct it, rectify it later. So whatever you feel is the most appropriate answer, just select that. But yeah, there is a possibility that the answers options given might be incorrect.
Right, but I just wanted to confirm, like the error, this thing that V plus or minus in the mu. If you just calculate it on paper, don't show it to anyone. It's coming round integer. It's not in 0.5 or anything, and we are subtracting it from 350 basically. So it should be a round number. It should not be having any kind of decimals.
Okay, I see. Okay, there are chances. Okay, but what was the like? Are you taking the sample size into consideration?
Sample size is 64. Under root of that is 8.
Yeah, and then what is the population standard deviation?
100.
Okay,
100
so
divided by 8.
Will it be?
But then we are also taking that multiply by 2 for 95% confidence level. Right, so it will be around this thing.
Okay, okay. Let us. No, but yeah. Okay, so yeah, I think I just mentioned that x bar minus sigma by root n. It should be x bar minus alpha times the sigma by root n, and so on. So yeah, alpha is given to you, is it?
Alpha is not given as such, but they are asking at 95% confidence level.
Okay, let us go back. Maybe I am getting confused. Wait a second. Is my screen still visible?
Yes, it's visible.
Yeah, Z, sorry, not alpha, Z.
Okay.
Yeah.
Z.
Yeah, so x will be x, like confidence interval will be x bar plus minus z into s by root n. So confidence interval for mean sample, like population mean. So you'll have to take this z into population standard deviation. Here it is sample standard deviation, but you can take
Okay.
sigma over. So
Right.
yeah, just like plug those values in this formula. We will
Right. I got
discuss this in detail later in the next session.
it. Right. Thank you.
Yeah, welcome. Any other queries? We'll discuss this confidence interval and other concepts in the next session. So how can I be able to communicate with you directly? Sorry, Tama, I hope that's the way you pronounce. Like I won't be available outside of this like sessions because I have some other commitments as well. So yeah, sorry for that. Like I'll be restricted only to these sessions. Yeah. You can definitely ask me any queries during the session, or maybe you can put a comment on YouTube and maybe I'll try to explain that in the next session, or I'll try to answer it over there on that YouTube comment itself. But yeah, I may not be checking the YouTube comments very frequently, so yeah, please feel free to ask me during the sessions. Okay, I hope the session was helpful and you learned something from these sessions, and if I have made any mistakes, apologies for that, and please feel free to correct me if I am wrong anywhere. So
Thank you for the session, Sash.
yeah, this was all about it, and yeah, please let me know any feedback, like whatever you may need, like in the next session, like if something was not covered here from the previous week and you had any queries, so please feel free to ask in the next session. So thank you everyone for joining. I'll end the session over here, and I'll be uploading the recording shortly to my YouTube channel. I'll share the link again over here in chat. Okay, here you go. So thank you everyone for joining. I'll end the session now.
Thank you, sir.
Thank you.
Thank you.